Hey, Canyon. Say hi to Canyon. Hi, Canyon. Okay. Anyway, so once again, if you have a weak acid, you're starting with a weak acid, you're going to get a conjugate weak base. And if you have a weak base, you're going to get a conjugate weak acid. So if your acid has the proton, H plus, or HA, it's going to dissociate to H plus A minus. Makes sense, right? Now, if your base is a weak base, it's just B, and it's going to be in equilibrium with BH plus OH minus. Okay? And again, when you see an H plus, you can go ahead and substitute the hydronium ion. It's basically the same thing. So far, so good? Well, what happens when you put the conjugate in water? We know if you put an acid in water, it's going to form the weak conjugate base, and it's going to be acidic because the proton is going to be released from the HA, a few, and you're going to leave A minus behind. This is going to be an acidic solution. Now, if you have a base, you put that in water, the base takes a proton from water, leaves hydroxide behind, and this is going to be a base. But what happens if you just put A minus in water? What's that gonna do? That's not a rhetorical question I'm asking. What do you think is gonna happen? If we put an A minus in water without the HA, just the ion, just put the ion in water, what's gonna happen when it finds water? It's gonna take a proton, exactly. It's gonna form HA, the, what do we call this? Undissociated molecule, and some hydroxide. Now here's the important thing. Where does the equilibrium lie for the weak acid? Does it lie mostly with the reactants or the products? For a strong acid, it relies entirely with the products. But for a weak acid, it lies almost entirely with the reactants. Our K value is going to be much smaller than 1, which means we're going to have a teeny numerator and a big denominator. Remember, products over reactants? So you're going to have your Ka, that's going to have a teeny tiny H plus, and a teeny tiny A minus, and a gigantic HA. The equilibrium lies primarily with the undissociated molecule. This is super important because that's the biggest difference between a strong acid, which goes all the way to the products and stays there, and a weak acid, which shifts back and forth in equilibrium, but primarily there's more undissociated molecules than ions. The same thing happens with Kb. If you look at the Kb for a weak base, the Kb, oh, that's a B. The Kb is much, much less than 1. So you can write it as Kb with a teeny tiny BH plus and a teeny tiny OH minus and a big undissociated molecule B. Put that chair down, it's bothering me. I feel like you're going to hit it with your hand and knock it over. It's going to fall on with Bennett and rain. Weird. Okay. Is that clear? Okay, so then I asked you, what happens if you just add the A minus to water? No HA, just the A minus. For instance, classic weak acid is acetic acid, H2 or HC2O3. There's acetic acid, and it breaks down into a proton plus the acetate ion, which is C2, H3O2 minus. This is the ion that you taste in vinegar. Okay. So where does the equilibrium primarily lie? With the undissociated molecules. So the equilibrium primarily lies with the reactants. But if you put in something like sodium acetate, you take NaC2H3O2 and add that to H2O, the anion tries to form the undissociated molecule. In other words, the anion, which is just this is A minus, grabs a proton to form HC2H3O2 and hydroxide. Remember, equilibrium, we like to think about, we're Americans, we read from left to right. Everything goes from left to right. But in equilibrium, it goes both ways. It goes to form whatever is more thermodynamically stable. And what is most thermodynamically stable in water is the undissociated molecule. So if you put an ion in, it's going to grab a proton from water and form HC2H3O2. Now, does HC2H3O2 make an acidic solution? No. The proton does. So if you put the conjugate of an acid into water, it will form the HA. The HA does not produce an acidic solution. It is the H plus that forms an acidic solution. So if you put the conjugate of an acid in solution, you will get its acid with hydroxide, because the conjugate of a weak acid is a weak base. Capiche? Okay. Same thing happens for weak bases. If you take the BH plus, and the classic BH plus that we use is NH4 plus. If you take NH4 plus and you add that to water, this is the BH plus. What is it going to do? Ignore the 3D printer. It's just I'm testing. It's going to donate, exactly, it's going to donate a proton and form H3O plus NH3. And again, the undissociated molecule is more thermodynamically favored, more thermodynamically stable than the ions. So if you put the base cation into water, it's going to form the proton, H3 plus, and the undissociated base. So if you have a weak acid, it forms a weak base and H plus. If you have a weak base, it forms a weak acid and OH minus. But if you just take that conjugate and put the conjugate in water, it reforms the acid or the base, leaving the proton or the hydroxide behind. Cool? Questions? Let's look at specifics. I'm sorry I made this go away. I apologize. I can figure out how to. There's a way to basically come back to what you were writing.
Yeah.
Yeah, there is a screenshot button. Nobody knows where it is, but there is a screenshot button.
There wasn't undo at the bottom that you hit.
Why is it? Oh, here. It's like, hey, let's look at your pictures. There's that one. Swipey, swipey. Swipey, swipey, swipe. Nope. Maybe, nope, that one, no. Okay, well, figure it out eventually. For now, I can't struggle with this anymore. So we're just gonna get out of there. Okay. All right, so NaCl. You gotta split the ion into its pieces. You have Na and Cl. Okay. Does Na have any effect on acidic or basic solutions? Because when you put NaCl in solution, realize this is Na plus Cl minus. So does that have any effect on acidity or basicity? No, because sodium, listen carefully, is the conjugate of a strong base. So if you remember, NaOH is a strong base which forms Na plus OH minus. That's a one-way road. That is not equilibrium. That goes one direction and can't go back. You cannot take sodium, add it to hydroxide, and make sodium hydroxide. So the Na is the conjugate of a strong base, so it cannot form anything. It is neutral. In summary, the conjugate of a strong is neutral. Conjugate of a strong acid, neutral. Conjugate of a strong base, neutral. Conjugate of a broken printer, crap. Stop being so silly. Got a damaged printer. I think I can fix it. I hope I can fix it before I destroy it. I'm getting really angry. Check out the window. Anyway, does that make sense? So the sodium is the conjugate of a strong base, so it's neutral. The chlorine is the conjugate of a strong acid, so it's neutral. So if you have HCl, our happy strong acid, it forms H plus Cl minus. So the chlorine is a conjugate of a strong acid. Again, one-way road. Can't go back. It's not equilibrium. Strongs go one direction, they dissociate, and that's it. You cannot reform a strong acid or reform a strong base. So you split it in half and say, all right, sodium is the conjugate of a strong base, therefore a neutral ion. Chlorine is a conjugate of a strong acid, therefore a neutral ion. If you are comfortable with this idea, give me a thumbs up. Okay. Then we get to sodium bicarbonate. This is sodium bicarbonate. The bi means there's a hydrogen in there. So that's sodium bicarbonate. Sodium carbonate is Na2CO3. That's sodium bicarbonate. So you think, what happens to sodium bicarbonate? Well, it splits into sodium because sodium dissociates completely and it leaves behind what's called the bicarbonate ion. That's step one. Step two. That bicarbonate ion is in equilibrium with carbonic acid, H2CO3. That's the stuff that they put in, when you put carbon dioxide in water, it forms carbonic acid, like soda pop. Carbonic acid, H2CO3. That's carbonic acid, a weak acid. So if carbonic acid is a weak acid, where does the equilibrium primarily lie?
In the dissociated.
Left or right?
In the reactants.
That's a dissociated ion. The equilibrium always lies with undissociated. For a weak acid or a weak base, the equilibrium always lies with the undissociated molecule, which is that. But where did that proton come from? From water. You put it in water, it's going to take that proton, and if water loses a proton, what's left behind? OH. This one is a base. It is a base because it is the conjugate of the weak acid H2CO3. How are we doing? Okay. Hopefully we don't have to talk about NaOH at all. That's a strong base. Strong bases dump the hydroxide right into water, easy peasy. Okay. Strong acids dump the protons right into water, easy peasy. So any group 1 metal plus hydroxide is going to be a strong base. Most group 2 metals plus hydroxide are going to be strong bases. So lithium hydroxide, sodium hydroxide, potassium hydroxide, rubidium hydroxide, cesium hydroxide, and it could go on, francium hydroxide even. Those are all going to be strong bases because they have the hydroxide with them. Beryllium hydroxide, magnesium hydroxide, calcium hydroxide, strontium hydroxide are all going to be strong bases because they have the hydroxide with them. Good? Okay. On the acid side, hydrochloric, HCl, hydrobromic, HBr, hydroiodic, HI, and if we actually cared about acetine, we could say hydroacetinic acid, but we don't care about that because it's it just breaks down, we don't play with it. But those three are strong acids that just dump the protons right into solution. Now HF is special. HF is a weak acid. It's a very robust weak acid, but it has a K value that is less than 1, so we consider it a weak acid. And the reason that is because the fluorine is crazy electronegative and teeny tiny. So it doesn't want to give up. It has trouble giving up any proton or any electrons of any kind. But yeah, so here we go. Are we cool here? Okay. And then we get this one, sodium phosphate. It has the same situation as the previous one, where this is going to break down into Na plus H3PO4 minus. No, that's the wrong H. Nope, this one, boop. There we go. H2PO4 minus, and it is going to take a proton to form H3PO4 minus. This is phosphoric acid. So H2PO4 is the anion of phosphoric acid. If you put the anion in water, it's going to grab a proton from water and produce H3PO4, that should not be a minus, plus your hydroxide. So that's the pattern. If you find in your compound a conjugate of a weak acid, that ion will form its weak acid, leaving hydroxide behind. If you find in your compound the conjugate of a weak base, that ion will form the weak base, leaving a weak acid, leaving hydrogen ions behind. How are we doing with this? Because that's the bulk of this. Okay, so again, sodium acetate, that's the classic. Sodium acetate is going to break down into sodium. Again, when I say classic, like probably a third of all the acid-base questions use acetic acid. All right, cool. Everybody loves acetic acid because it's just vinegar. That's going to form H2. That's going to form this is minus HC2, H3O2 plus the hydroxide ion. Okay, the one that I was really surprised about is calcium oxide. If you put calcium oxide in water, the oxide ion is less stable than the hydroxide ion. So calcium 2 plus O2 minus, eek. The calcium part is going to be neutral. It is the conjugate of a strong acid or strong base. But if you add this to water, the hydroxide really doesn't want to be there. I'm sorry, the oxide really doesn't want to be there. So what forms is CaOH2 aqueous. And then obviously to form that, you need to pull some protons from hydroxide, and then the hydroxides also donate to water. So an oxide is always strongly basic. Okay? As long as it's not a metal oxide, as long as it's not a D-block metal oxide. Gesundheit. If it is a group 1 oxide or a group 2 oxide, Lithium oxide will form lithium hydroxide. Potassium oxide will form potassium hydroxide. Magnesium oxide will form magnesium hydroxide. But iron oxide will not. The AP does not touch the D block for acid base, because there's all sorts of crazy funny stuff going on in D block. When they do acid base, it's always the outsides of the periodic table. Bases on our left, acids on our right. We don't care about the middle. We never use the middle. All right. So the one that should have made a strongly acidic or a weakly acidic solution should have been this one. Because just like up there, the ammonium is NH4 plus. The ammonium and the nitrate dissociate. The nitrate does nothing because the nitrate is the conjugate of nitric acid, a strong acid. Oh, minus. Okay. So nitrates are neutral because they are the conjugate of nitric acid. So the nitrate should do nothing. However, the NH4, when placed in water, the NH4 should donate its proton, forming the undissociated NH3 and H3O plus. So this one should have been acidic. I don't know why it wasn't. I can't explain why a bunch of you got green on it. All right, questions? All right, let you bang on your calculator for a little bar. Bang on your keyboard for a while I check, see if there's nothing else we can go over. Discuss acid bases. Yeah, that's all we can go over.
Is the sodium phosphate supposed to be basic?
Hydrogen phosphate?
Oh, yeah.
Yes, it's supposed to be basic because the H2PO4 minus takes a proton from water to form H3PO4. Oh, right, because it's triprotic. Okay, I'm glad you mentioned that. Are we comfortable with this? Okay, new bomb is acidic, and this is why. Brain bomb, here we go, and clear all, yep. Let's focus just on the triprotic hydrogen phosphate, or hydrochloric. Okay, so H3PO4. This is phosphoric acid. This is a weak acid, a very robust weak acid. But it's also what we call a triprotic acid. So it's going to be in equilibrium with H2PO4 minus, which is also going to be in equilibrium with HPO4 2 minus, which is going to be in equilibrium with PO4 3 minus. I know it's bonkers. Triprotic. So when you look at these, you have to ask yourself, what is going to be more thermodynamically favored? Well, the H3PO4 is a weak acid, which means the H2PO4 minus is a weak base. But it can also donate a proton, making it also a weak acid. Yeah. There's a term for this. It's called amphoteric, when you can release or gain a proton. Like water is amphoteric, form H2O plus or OH minus. So if it acts as a base, then if you put it in water, it's going to form an acidic solution. If it acts as a weak acid, then it can still donate its proton and form this, the HPO4 2 minus. And it does that by taking a proton, making this solution basic. So between the two, you found that this was more likely than this, right? You found
Orange.
it was orange?
Yeah.
Okay, then you found that this was more likely than this. Okay. So the H2PO4 minus took the proton to form the H3PO4. We're going to start attaching numbers to this concept tomorrow. We're going to look at actual numbers of Ka and Kb, and then talk about which of these weak acids is more robust, which of these weak bases is more robust. Questions? Okay, I've talked a lot. I don't want to talk anymore. So you guys work on that lab, and I will say bye-bye, Kenyon. Bye-bye, Kenyon. Streaming. Bye-bye, streaming. Bye, stream.